Welcome to online lecture series in organic chemistry, and we are discussing the chapter electronic spectra of complexes. In earlier video we have started the electronic states, and electronic states, these are the energy levels resulting from the electron-electron interaction and magnetic interactions. And the electronic states are defined by four important quantum numbers: resultant spin quantum number, resultant orbital angular quantum number, spin multiplicity, and total angular momentum quantum number. In last video we have seen about the resultant spin quantum number. In this video we are going to discuss the resultant orbital angular quantum number, that is L, or coupling of orbital angular momenta. So here the azimuthal quantum number, that is small l, it is associated with or related to the orbital angular momentum of an electron or single electron, whereas the resultant orbital angular quantum number, that is capital L, it is associated with the orbital angular momenta of a set of electrons. When there are more than one electrons, then instead of azimuthal quantum number there is a consideration of the resultant orbital angular quantum number, that is capital L. And the resultant orbital angular quantum number, it is the algebraic sum of individual the orbital angular or azimuthal quantum number values, that is small l. So it is given by L is equal to summation of L values, and here each resultant orbital angular quantum number value ranges from L1 plus L2 to L1 minus L2, where L1 and L2, these are the individual azimuthal quantum number values for different electrons. When there are two electrons, then L1 it is the azimuthal quantum number value for first electron, and L2 it is the azimuthal quantum number value for second electron. So this is the L is equal to L1 plus L2 to L1 minus L2. And most important thing is the successive L values differ by 1. Successive L value differ from each other by 1, and these values are whole numbers including 0, that is 0, 1, 2, 3, 4, 5, 6, etc. Now value of L, as I said, it differ from each other by 1. If it is 0, then the state symbol is S, capital S. If L is equal to 1, then it is P, capital P. If L is equal to 2, then capital D, and not small d, capital D. If L is equal to 3, then F, then G, H, I, and so on. So these are the L values, that is 0, 1, 2, 3, 4, 5, 6, and these are the state symbols, that is capital S, P, D, F, G, H, I, etc. Now we will take example how to find out the state, or how to find out the term or state for a simple electronic configuration. Consider the simple configuration, that is P2. There are two electrons in P subshell. These are the 3 p orbitals, px, py, pz, and 2 orbitals contain single electrons. Now for first electron, value of L1, it is 1. You know, for p subshell L is equal to 1, and both the electrons present in p subshell, and therefore for each electron value of L is 1. So L1 that is equal to L2 that is equal to 1. For first electron value of L is 1. For second electron value of L is also 1. Why? Reason is both the electrons present in p subshell, and for p subshell azimuthal quantum number value is 1. For s subshell L is equal to 0. For d subshell L is equal to 2. For f subshell L is equal to 3. And therefore when these two electrons present in p subshell, value of L is 1. So L1 equal to L2 that is equal to 1. Meaning of this is for first electron L is equal to 1. For second electron L is equal to 1. So as per this formula, L is equal to L1 plus L2 to L1 minus L2. Let us find out the resultant orbital angular quantum number. So when we substitute the value of L1 and L2, then 1 plus 1 to 1 minus 1. It means value of this resultant orbital angular quantum number ranges from 2 to 0. 1 plus 1 it is 2 and 1 minus 1 it is 0. And as I said earlier, each L value differ by 1, and therefore possible L values are 2, 1, 0. They differ from each other by 1. And when L is equal to 0, then the state symbol it is S. When it is 1, then state symbol is P, and when L is equal to 2, then state symbol is D. And therefore corresponding state symbols D, P, S. It means for P2 configuration, these three state symbols are possible: D, P, S. Consider another example, that is the D2. It means two electrons present in D subshell, and for D subshell value of azimuthal quantum number, that is L, it is 2, and therefore L1 that is for first electron and L2 that is for second electron, value of azimuthal quantum number is 2, because both the electrons are present in D subshell, and therefore L1 that is equal to L2 that is equal to 2. So formula L is equal to L1 plus L2 to L1 minus L2, then 2 plus 2 to 2 minus 2, 2 plus 2 it is 4, and 2 minus 2 it is 0. So value of this L, that is resultant orbital angular quantum number, ranges from 4 to 0, and each value differ from neighboring value by 1, and therefore possible L values are 4, 3, 2, 1, 0 or 0, 1, 2, 3, 4, and corresponding state symbols are G, F, D, P, S. G, F, D, P, S. Now consider one more example, that is F2 configuration. It means there are two electrons present in F subshell. There are 7 F orbitals, and for F subshell value of azimuthal quantum number is 3. Again L1 that is equal to L2 that is equal to 3. It means for first electron L value is 3, for second electron value of azimuthal quantum number is 3. So L1 equal to L2 that is equal to 3, and capital L that is the resultant orbital angular quantum number, it is equal to L1 plus L2 to L1 minus L2. Again when we substitute the value of L1 and L2, then we can write 3 plus 3 to 3 minus 3. 3 plus 3 is 6, 3 minus 3 is 0. So value of L ranges from 6 to 0. These values are in between 6 to 0, and the possible L values are 6, 5, 4, 3, 2, 1, 0, because each L value differ from its neighboring value by 1, and these are the possible L values, and corresponding state symbols are I, G, I, H, G, F, D, P, S. Or from this side when we have L values, that is 0, 1, 2, 3, 4, 5, 6, then possible state symbols are S, P, D, F, G, H, I. So these are the state symbols. Now next important quantum number, that is the spin multiplicity. The spin multiplicity, it is ms equal to 2s plus 1, where s is the resultant spin quantum number. So we can find out spin multiplicity from resultant spin quantum number or number of unpaired electrons. Spin multiplicity is number of unpaired electrons plus 1. Now spin multiplicity, it is the number of orientations of spin along the direction of magnetic field. If there is no any unpaired electron, so number of unpaired electron is 0, then resultant spin quantum number, that is S, capital S, it is 0. And spin multiplicity, that is ms, it is equal to 2s plus 1. The value of this capital S, it is 0, and therefore applying this formula 2s plus 1, we have a spin multiplicity 1. And name of this state, it is singlet. It means if there is no any unpaired electron, all the electrons are paired, then resulting state of configuration or electrons, it is called a singlet. Now consider there is one unpaired electron. Resultant spin quantum number for one electron, if it is spinning clockwise, then the value of S, it will be plus half. So resultant spin quantum number is the algebraic sum of individual spins, but there is only one spin value, that is half, and therefore resultant spin quantum number, it will be half. Spin multiplicity, applying this formula 2s plus 1, so value of S is half, so half into 2, that is 1 plus 1, it is 2. So spin multiplicity is 2, and name of state, it is doublet. Similarly, consider two unpaired electrons. For each unpaired electron, individual spin value is half, and resultant spin quantum number, it will be half plus half, that is equal to 1. And spin multiplicity, using this resultant spin quantum number, actually the value of capital S, it is 1. So 1 into 2, that is 2, plus 1, that is 3. So spin multiplicity is 3, and name of this state, it is a triplet. It means there are two unpaired electrons, then it is called as triplet. Similarly, when there are three unpaired electrons, then the resultant spin quantum number, half plus half plus half, that is equal to 3 by 2. And spin multiplicity, using this resultant spin quantum number, we can find out value of S is 3 by 2. So 3 by 2 into 2, that is equal to 3 plus 1, it is 4. So spin multiplicity is 4, it is called as quartet. And if there are 4 unpaired electrons, then the resultant spin quantum number, so add the half values like this, half plus half plus half plus half, that is equal to 2. So this is the resultant spin quantum number. And spin multiplicity, now value of S here, it is 2. So 2 2s are 4 plus 1, that is 5. So spin multiplicity is 5, and meaning of this is, or name of this state is quintet. It means when there is no any unpaired electron, the name of state is singlet. When one unpaired electron is there, then it is doublet. When two unpaired electrons are there, then it is called as triplet. When there are three unpaired electrons, then it is called as quartet. And when there are 4 unpaired electrons, then it is called as quintet. Now spin multiplicity also be calculated by using, directly by using unpaired electrons. So number of unpaired electrons plus 1, that is the spin multiplicity. For example, if there is no any unpaired electron, so value of n, it will be 0. So 0 plus 1, that is 1. When one unpaired electron is there, 1 plus 1, that is 2. So here, if there are 2 unpaired electrons, then 2 plus 1, that is 3, and so on. So this is how to find out the spin multiplicity. So in this way, here we completed the one more quantum number, that is spin multiplicity.